Okay, greetings again, class. So this is our last topic on the application of the definite integral, and that is the hydrostatic force. Okay, after this, we'll be discussing multiple integration, and that's it for you for this semester in integral calculus. It's very important that in the course of our discussion, you are not sleepy, you have a clear state of mind. That way, whatever I'm discussing here would be received by you uh, 100%, if not 90%. What I'm trying to say is that you will understand what I'm going to discuss. This will be one challenging topic to discuss and make simple, just for the sake of having to be able to apply the concept of the definite integral on the determination of the hydrostatic force. So I hope you have a full stomach, you are not sleepy, and that you are in the mood to learn. Okay, not just simply listen to this, but really learn from the discussion. Okay. What is our learning objective for this particular topic? So we are guided by simple two learning objectives, and that would be the definition of the hydrostatic force. So you as students should be able to define it, and then should be able to determine it using a definite integral. Now, since we are required to determine the hydrostatic force, we need to be able to define what is hydrostatic force. So the force that is exerted on anything that is submerged, in our example here, it's a plate, due to the pressure of the fluid in the container in which our object, or in this case our plate, is submerged to, is called the hydrostatic force. So hydro meaning water. So if anything is submerged in water, it will be subjected to what we call the hydrostatic pressure. And that hydrostatic pressure is due to what we call as the hydrostatic force. Now, let's say, for example, in our illustration here, we have water, of course, and we have submerged this slab into water. So the force, the hydrostatic force, is in this direction, acting on this face of the plate. Now, this particular hydrostatic force is directly proportional to the hydrostatic pressure, meaning the pressure that is exerted by water on the face of this plate. Now, you have learned from physics that we have defined pressure as equal to the force per unit area. And that particular force has to be perpendicular to the area in which it is applied to. So this F here that you see is what we call as the hydrostatic force in this particular scenario. The force that is exerted on the face of this plate by water when this plate is submerged on it. Now, you could see that this is the width of the plate. This is the Y. This is how we measure Y, from starting from the topmost part of the plate. This is the height of the plate. Now, if we're going to select or draw a particular differential element here, a dA, a differential area in here, that would be this differential area. And as we go down, this differential area is fixed. So since we have a rectangular face, the differential area is fixed. However, as we go down, we will learn that pressure increases because the distance from the top of the plate going down increases. So why we say the pressure is increasing, we also say that the force is expected to increase as well, specifically the hydrostatic force. Why am I saying that when pressure is increasing as we go down, hydrostatic force is also increasing? It's because from this particular formula of the pressure being equal to F divided by A, we get to know that F is directly proportional to pressure. So if pressure increases, the force increases, or these two are directly proportional, referring to the hydrostatic pressure and the hydrostatic force. That is why in most cases, when we discuss hydrostatic force, the concept of the pressure or the hydrostatic pressure is also touched. Okay, now to move smoothly to the sample problems later on that I'll be discussing, first, if we have, let's say for example, d meters below the surface of this particular slab in here, then we say that the hydrostatic force is given by, or the hydrostatic pressure rather, is given by the product of the density, the G, and the D, where rho is the density of the fluid and G is the gravitational acceleration. Now we're going to assume that the fluid in question is water because we're talking about hydrostatic force. And since we're going to be using most of the time here in our class the metric systems, although we can also have the English system, when we speak of density of water in the metric system, that would be 1,000 kilogram per cubic meter. And the gravitational constant or acceleration is 9.81 meters per second squared. Now we are to assume that a constant pressure is acting on a surface with area A. Then the hydrostatic force that acts on the area is said to be given by this formula. Okay, that is why you have here F is equal to PA. Now, what about this particular differential area? Because you're going to choose this differential area here, dA. If you look at it, it's the product of the W and the dy. Because everything here in this phase will have a length or a width W. Okay, if this is the length and this is the width, so then this would be all fixed at W. However, the dy is different. So it depends on the location of this particular differential area. Now, if we go back to our formula here on top where F is equal to PA, and if we're going to differentiate the left side and the right side of this equation, and pressure is constant, then we have dF is equal to P dA. Pressure is constant, that is, we talk about pressure being constant, then we have it as PdA. However, in the case of hydrostatic pressure, if you were listening a while ago, if pressure is not constant, it would be dependent on the distance of this chosen differential area from the top of the plate. We know as we go down, this pressure increases because this D, and this Y here are the same. They increase as we go down from the top of the plate to the bottom of the, let's say, the container where this plate is submerged into. So we change now the P, which we assume to be constant, in the expression in which the D, the distance of the topmost part of the plate to the differential area chosen, is varying. So that D, this D now, was changed to Y. Because in here, in our illustration, it is Y. So we write the P as rho GY W. Now, where is this W coming from? You get to see this one here. W dy is your dA. So this dA here was changed to W dy. So this is the entire dA. The dA that you have here was placed in here and the W dy substituted. If pressure is not constant, as I have mentioned, then we change this pressure in terms of the formula rho GD, where D now was changed to Y, because this D represents the distance of that chosen differential area from the top of the plate, which is in our illustration here is equivalent to Y. So the hydrostatic force or the differential of the hydrostatic force will now be equated to the product of rho G W Y dy. In the case of our simple illustration here of this slab that was or that is being submerged in water. Okay, so that's hydrostatic force. the expression for the differential of the hydrostatic force, which will allow us to solve for it when we integrate the left side and the right side of this equation. Now let's go to specifics. That way you will fully grasp how is the concept of integral calculus, specifically definite integral, applied to the determination of the hydrostatic force. Now, in our first example here, you are to determine the hydrostatic force on the triangular plate. This is our triangular plate. This is the water surface. Our triangular plate is 6 meters on top, 4 meters going down. So the depth of the plate or the height of the triangular plate is 4 meters. It is submerged in water as shown. So this is understood to be all water. This is the water surface. The very first thing we do when we solve problems concerning hydrostatic pressure or hydrostatic force is that we identify the axis, or we place our axis in such a way that integration later on would be easy. Now, the proper identification of the location of the axis comes with experience. What do I mean by that? You will learn a lot on how to properly set your axis as you go along practicing solving problems on the topic of hydrostatic force. Because at times, learning by discovery is learning with more substance rather than just listening, or rather than just reading. So when you do it on your own, that's when you discover that probably at first try, you will learn that this is not a good orientation for my axis for this particular topic. I'd rather change my orientation to this because it would make it easier for me to place in the differential element that I have chosen and easily, of course, represent the correct integral. I hope you get or you understand what I mean. The proper placement of the ordinate axis or the coordinates or the x and y axis when you draw your particular figure in determining the, let's say for example, the hydrostatic force for a particular problem comes with experience. So you really have to read a lot, study a lot, and practice solving a lot. That way you will have the, let's say, the skill of having to write down the correct axis orientation. Now, in this problem, it is suggested just for this problem. Actually, you can change the orientation of the axis to any orientation that you want as long as you can properly write your integral based on the orientation that you have chosen. So the first thing to do here is set up an axis system. Now, let's redo the sketch above. So you have to redo the sketch above with the following axis. Now, in this sample problem, we're used to using the vertical axis as the y-axis. But in this problem, the vertical axis was presented in the form of an x-axis. So this is your x-axis rather than the y-axis. And it is said to be 4 meters from the water surface. So then, this must be your 0 part. And then as you go down, that is your 4. So take note that when you go down here, it should be negative. But in this case, it was measured as positive. And instead of labeling this as y, it was labeled as the x-axis. Now, let's move on. Now, so we are going to orient the x-axis so that the positive x is downward and x is equal to 0 corresponding to the water surface, and x equal to 4 corresponds to the depth of the tip of the triangle. So that was explained already. Now we break up the triangle into n horizontal strips. So you placed horizontal strips in your triangle. You can have one here also. You can also have another one in here. And as such, you can visualize that this entire triangle of yours is made up of these rectangular small strips. Okay? Now, each of these particular strips that you have drawn will have an equal width of delta x. If this is x, then the width would be delta x. So when you divide or when you write these strips here for your triangle, make sure that these strips are assumed to be of equal width delta x. In our usual orientation, this delta x is actually delta y because we set the vertical axis as y. Just in this problem, we represented it as delta x. Now, in each interval, we can have here from the top going to this particular line here on our differential element, that would be distance x sub I. That would be your x sub I. And as we go further down, the lower part of the rectangular horizontal strip is you have xi, x sub I. Okay, so you have x sub I minus 1 and x sub I. So this is your x sub I and this is your x sub I minus 1. You have to choose any point which is x sub I. So this is x sub I. And if your differential element is written here, the topmost part of that differential element, horizontal strip, will also be x sub I. In this case, it's with an asterisk. In order to make the computations easier, we're going to make two assumptions about our strip. And this is very important. This is the same assumption that we made when we use the process of approximating the area of a non-elementary integral in the topic of numerical integration. If you recall, we have two techniques there, Simpson's rule and trapezoidal rule. Now, in one of those two topics, we have assumed that our differential element is a perfect rectangle. Okay, we have assumed that it would be more or less a perfect rectangle and that the sum of all these rectangles would be approximately equal to the area of the curve, which is represented by a non-elementary integral expression. Okay, that's just a review on that particular topic. So in order to make the computations easier here, we're going to make two assumptions about this strip. First, we will ignore the fact that the ends are actually going to be slanted. So they're not straight here, but they will be slanted. So you're going to ignore that one and assume that the strips are rectangular. If your delta x is sufficiently small, this will not affect our computations that much. So we know that as we make this very small, this slanting would be very negligible. And as such, the area that we're computing would be closely, if not equal to the area of a rectangle. Now, the second assumption that we will make is that delta x is small enough that the hydrostatic pressure on each strip is essentially constant. If we make this small enough, the hydrostatic force, rather pressure on each of the strip will be essentially constant. And in our drawing, if this is our drawing, this is our strip. This is our representative strip. So take note, your assumption. You assume that your rectangles are very small or very thin. That way the ends will not be slanted. And the second is that since it's very small, the hydrostatic pressure on each of the strip will be essentially constant. Okay? If we will use the principle of similar triangles, okay, let me annotate here. If we will use the principle of similar triangles, we will have a bigger triangle. You have a 3 and a 4 for this big triangle. And you have this small triangle here, which is A, and this is equal to 4 minus x sub I. This is x sub I from here to here, and this one is 4. The entire length is 4 minus x sub I. By the way, this is your x sub I. Okay? Until the middle portion of this very thin rectangular strip. We assume very thin. So if it's very thin, the middlemost portion of that would be more or less the x sub I that I have mentioned a while ago. But nonetheless, this will be the location of the x sub I. So if this is x sub I, then this would be, if this is the entire shall I say, depth of your triangle, then that would be, if this is 4, then this one here from the center going down would be 4 minus x sub I asterisk, and that's it here. If you do similar triangles, 3 over 4 is to a over 4 minus x sub I with the asterisk. And we will have an expression here for the a in terms of the x sub I, or simply the x. That a is just 1 or half of the length of this horizontal strip that you have drawn. Okay, now we will continue. We'll clear the drawings here and we will continue to the next slide. And now, since we are assuming that the pressure on this strip is constant, the pressure is given by, again, we go back to rho GD, and our D, remember in the first slide, the D is represented as Y because it's in the usual orientation where in the vertical axis is Y. Now in this problem, we change it to X, then we change it to X sub I. Okay, so the pressure then, which is varying in terms of the depth of the strip in which you have chosen, would be 1000 for the density, 9.81 for the G, and X sub I for the location of that very thin horizontal strip from the top. So this is your pressure expression, which is dependent on X sub I. So if the hydrostatic force is defined as the product of the pressure times the area, you need to copy this expression for the pressure, and that would be in here. It's copied already. Okay, that's your pressure. What about the area? The area of this thin strip, horizontal strip, would be 2a times the delta x. This is the delta x. In the usual representation, it should be delta y. So you could see here that you have 2a delta x. Okay? Now, we copy the 2810xi in here. We have the 2, and the a here that you see was changed to the a expression that we got in the previous slide using the principle of similar triangles. So we took it from the other slide. Then you have delta x. So if we will simplify everything, you multiply this 9810 to 2, that would be 19620, copy x sub I asterisk, copy this expression, and you have delta x. This is your hydrostatic force. So copying all of this and changing the x sub I to x and the delta x to dx, this would be your expression for the hydrostatic force exerted on any of the chosen horizontal strip on this triangular plate that was submerged. So since we want to account for this hydrostatic force, the total hydrostatic force for this entire face, for the entire triangular face or triangular plate, then this dx that we have here, which is this one by the way, should tell us that our limit of integration would be starting from 0. This is where our 0 is, to 4 as we go down. So as we go down, we expect that hydrostatic force will be increasing. So this would be our complete integral now. Now, the hydrostatic force that is exerted on this triangular plate is equal to 156,960 newtons. Now, this part here will just simply use power rule. Actually, you need not even worry about the technique that you will use because you're dealing with a definite integral. Your calculators can do the rest of the work for you. What is challenging here is in setting up the expression for the hydrostatic force because the rest can be done by your calculators. If this expression is not a definite integral, though it's impossible because we cannot get the actual value of the hydrostatic force if this is not a definite integral, then there's really a need for you to show the procedure, the process of determining the answer. But since this is a definite integral, actually, you need not write this one. You need only, after writing this, you need only to write the final answer. unless otherwise the direction or the, shall we say, the instruction says that you have to show your complete solution. So then it will not be as abrupt as writing the integral expression and the actual answer. It will require the justification of the actual answer, meaning you have to show the process of integration. So we will review. So you need to go back to the concept of the pressure, which is rho G Y. Y is the depth of the differential strip from the surface that is not submerged. Okay, because we know that this pressure increases as Y increases. Once you have the pressure, you multiply it with the area of your differential strip, whatever that may be. So there are two challenges here that I have seen: the correct representation of the pressure and the correct representation of that area, which will now be consisting, or which will contain, the differential of x. The differential of x should also tell you what should be the correct limit of integration or limits of integration when you already write it down in the form of an expression. Okay, so the same thing as what I have discussed in the topic of the work. It's very important that you know the expression of the representation of the work, the force, the distance, and then, very importantly, the limit of integration. So it's in here also. It's very, very important. Okay, let me clear the drawings here, and we'll have the next example. And this is the last. Now find the hydrostatic force on a circular plate of radius 2 that is submerged 6 meters in water. So this is the 6 meters that is mentioned. So this circular plate is submerged 6 meters, and the radius of the circular plate is 2. So this one is the radius, which is equal to 2. And by the way, this problem, it goes, this particular expression for the x here is already provided in the illustration. The relationship between x and y. Now, first, just like what we did in the first example, we're going to assume, or we're going to set our ordinate system, or our x and y axis. And in setting that up, in this particular problem, we're going to assume that the top of the circular plate is 6 meters under. The top of the circular plate is 6 meters under the water. This is your water surface here. Next, we will set up an x-axis system so that the origin of the axis system is at the center of the plate. So this is your 0 coordinate, so 0, 0. And we will use the usual way of representing the axis. Horizontal is x and vertical is y. So setting up the axis system up in this way will greatly simplify our work. So take note of this suggestion. Whenever you encounter submission of anything underwater, it's important that at the center of that thing, that's where your origin of the x and y axis should be. If it's completely submerged in water, so it's suggested in here because it makes things a lot easier to process or represent. And finally, we will split the plate into 2 horizontal strips, just like the triangular plate that we just finished a while ago. You will have horizontal strip here divided into 2, each with width delta y. So this is delta y. In the previous example, that's delta x, that's delta y. And we'll choose a point y sub I prime, or y sub I asterisk in this case, from each strip. So this is your y sub I asterisk. Now it's the middle, it's in the middle of this very thin plate. So somewhere in the middle here. So if this is y sub I asterisk, then the distance from the water surface from here would be 8 minus y sub I asterisk. Okay? This is the distance. D sub I would be 8 minus y sub I asterisk. So let's continue on the next slide, but before we do that, we clear our markings. So the depth below the water surface is d sub I, which is 8 minus y sub I asterisk. I mentioned that. And that in turn gives us the pressure on the strip. So the pressure on this strip is G, rho G di. Again, you have 9.81 times 1,000. So that would be 9810. And the di would be 8 minus y sub I asterisk. The area of this strip, since it's already presented here that this x is this one, so it should be multiplied by 2 for the length, and the width would be delta y. So I have already, so let me just write it here again. The width, this is the width, which is delta y. Now this is the area, and this is the pressure. Then the product of the two must be our hydrostatic force. So if we get the product of the two, all you have to do is multiply everything, and you place here delta y. So our force would be the limit of this particular expression. If we start with I equal to 1 up to n, where n is made as much as possible large, that way this particular rectangular strip would really be a rectangle. Because if you have it very large, if your n is rather very small and this would be very large, the ends of our strip will not be actually that of a perfect rectangle, similar to a perfect rectangle, but rather it would be curved. But if it's chosen to be very small, it would be approaching that of a real end of a rectangle. So this is the force that we have. Now notice that from the summation here symbol, the evaluation of the summation of the limit, you have replaced it with the integral expression. It's the same thing actually, only that the expression which has the y was written after the integral. Very important here for you to note would be the limit of integration. So it started with -2 because our radius is 2. And since this is where our Cartesian plane origin is, so this is 0 and this is 2. So if we are to sum up all the delta y's here, all the dy's, that will be starting from -2 to 2. So that's the purpose why you have to set up the center of your Cartesian plane of your coordinate axis on the center as well of your regularly shaped area. In this case, this is a regular area, uniform area rather, not regular, a uniform area because that it's that of a circle. So we set our center or origin of the x and y axis at the center of the same area. So this is now our integral, starting from -2 to 2. Okay, now it's based on the dy, which will sum up all the strips that you have here, that you will be making here for this particular circular plate. So if we will clear again our drawings and proceed, this particular integral away, by the way, can be right away integrated using your calculators. But in here, there's a suggestion on how you go about it. It's going to use trigonometric substitution and algebraic substitution. That way you'll be able to properly evaluate the two integrals. So the original integral was split into two different integrals, but actually the difference of these two is just equivalent to that particular original integral, so that the procedure or the complete solution of finding the value of the hydrostatic force can be presented. But again, I will stress that it's not needed because once you have set this up, as long as this is correctly done, there's no need for you to present this procedure here. Your calculator will just give you this answer right away. The calculator may not compute it right away. It will take probably a few seconds or some minutes, especially if the integral is not as simple as the one that's presented here, the original one. But your calculators can do that for you, okay? And I think the two examples here would suffice for the topic of the hydrostatic force. Should you have any questions, we're done with the application of the definite integral. Let me know. Drop me a line in Canvas or in our GC, or even privately through Messenger or my email. Okay, thank you class for listening. One more topic and we're done for the semester.